Inverse functions are functions that undo each other. Before we talk about what they are, let's just talk about how to find an inverse function. So step one is we are going to flip-flop our x and our y. We're flip-flopping the independent variable with the dependent variable. So f of x, that's our function output. We're going to turn that into the input, and the input becomes the output. So instead of y equals 3x minus 5, we have x equals 3y minus 5. That's step one. Step two is now we're going to isolate the new y variable, the new output variable. So to do that, we're going to add 5 to both sides and then divide by 3. So our y, now that it's isolated, is x plus 5 over 3, or 1/3 x plus 5/3. That does not look like an equal sign. And when we are noting an inverse function, we use, it looks like a -1 exponent, but it doesn't mean to the negative first exponent. That means inverse. So when it's on a function name, it means the inverse of f equals x plus 5 over 3. So let's do that one more time, and then we'll talk a little bit more about what an inverse is. So the original function is going to be 2x plus 4. I'm going to go ahead and graph that. That's going to be a prompt in a minute, but I'll go ahead and do that. So y-intercept of 4, slope of 2. I'm going to graph lots of points on here to get a nice straight line. All right, and then when we're finding the inverse, I'm going to flip-flop the x value and the y value and solve for the y value. So this time I'm subtracting 4 and dividing by 2 to isolate the y. So my y is x minus 4 over 2. Then I'm going to rewrite that as an inverse function. Because we're going to be graphing it, I'm going to write it in slope-intercept form. So my slope would be 1/2 x, and my y-intercept is -2. -4 divided by 2. So my y-intercept, I've got my slope of 1/2, and I'm graphing some points there. I said I was going to make a nice straight line, and these lines are not so nice and straight, but they'll work. So question, we graphed both the functions already. It says, what is the line of reflection? We'll get to that in just a second. Before we do, let's talk about ordered pairs for these graphs. So I don't have a whole lot of room here, but I'm going to try. So I'm going to have f of x, and I'm going to have the inverse of f of x. And I'm just going to name ordered pairs from each one of those functions. So like the blue function, the original function, f of x, has a point at 0, 4. It has a point at 1, 6. It has a point at 2, 8. Go in the other direction. We've got a point at -1, 2, at -2, 0, at -3, -2. We'll stop there for now. I'm going to do the same thing with my inverse function. So my inverse function, we had the y-intercept at 0, -2. Going to move right for a minute. So my next good point was at 2, -1. I had another good point at 4, 0. I'm going to move in the other direction. I've got a point at -2, -3. Another one at -4, -4. All right, and what I want you to notice about these is that if the point 0, 4 was on the original function, the point 4, 0 was on the inverse function. If the point 1, 6 was on the original, oops, I didn't write that one on here, but let's look at our red graph. I have the point 1, 2, 3, 4, 5, 6, 6, 1 was right there. 2, 8, I did not find 8, 2, but you can see that 8, 2 is on this one. Just like 2, 8 was on this one. Negative 1, 2, the inverse had 2, negative 1. Negative 2, 0, inverse had 0, negative 2. Negative 3, negative 2, inverse had negative 2, negative 3. So that is true of all inverse functions. The domain of one inverse function becomes the range of the other, and the range of a function, of an inverse function becomes, I did not say this right, but if you take an original function, its inverse, basically you flip-flop the domain and the range. I was getting a little wordier than I needed to. But the domain and the range, they flip-flop each other, and that's because inverse functions are a reflection over the line y equals x, always. Because that's true, because inverse functions undo each other, to verify that we have inverse functions, you take the composite functions of both ways, so f of g of x and g of f of x, and if they both equal x, then they are inverse functions. The process of showing that they equal x is called the verification process. It's kind of like a proof, but you don't have to get real wordy or anything. So if I'm going to show that f of g of x equals x, that means first I'm going to plug g into my f function. So here's what that looks like. I've got 3, and then where the x is, I'm going to substitute x plus 1 over 3 minus 1. When I go to simplify this, the 3's are going to cancel each other out. So I have x plus 1 minus 1, and x plus 1 minus 1 is x. That's what we wanted it to be. This always happens when we have inverse functions. So now I'm going to go the other way. I'm going to find g of f of x. So I'm going to plug f into g. F is my inside function this time. So where the x is, I'm going to plug in 3x minus 1. And then g has a plus 1 and a divided by 3. So if I'm going to simplify this, first I'm going to simplify the minus 1 plus 1. Those cancel out. And 3x divided by 3 is x. So both ways, when we put what we thought would be the inverse function into the other function, the original function, and vice versa, both times we got x. That means they are in fact inverses of each other, and this work is our verification process, proving that f and g are inverses of each other. That can be a little bit confusing, so let's do that again. So if I have two functions, f and g, so these are two different problems. We'll look at the left side first. I've got two functions, and I want to know if they're inverses of each other or not. So first, I'm going to plug one function into the other. I'll do g into f this time. So when I do that, I get x minus 5 plus 5, which is just x. Now I'm going to plug f inside of the g function. And when I do that, I get x plus 5 minus 5. And the 5's cancel, and we're left with x. So this time, yes, they were inverses of each other. F and g were inverses of each other. Over here, we're going to go through the same process. I'm going to plug g into f and make sure I get x. So I have 8 where the x is. I'm going to plug in the cube root of 2x, and then I'm going to cube it. Well, the cube and the cube root cancel each other out, and so we're just left with 2x in there, times 8 is 16x. In order for them to be inverses of each other, we should have gotten an x there, but we got 16x. So these are not inverses, because when we plugged one into the other, it didn't completely undo itself. We got 16x instead of just x. So F and G are not inverses. We don't even need to test the other direction. We don't need to plug F into G. We just know they're not inverses. So when we are dealing with nonlinear inverses, just because we have a function does not mean its inverse is a function. Let me show you an example, and then we'll come back to this slide and look at it. Let's say, ignore this part, ignore this limited domain for a second. Let's say we had the function f of x equals x squared. Let me make an xy chart for that. So if I plug in -2 for x, I'm going to get 4 for y, because -2 squared is 4. If I plug in -1, I get 1. If I plug in 0, I get 0. And really, I should have, instead of y, I should have called that f of x. My input is 1. My output is 1. My input is 2. My output is 4. So here's what would happen for the inverse function then. Or I should say for the inverse. So because we saw before that our inverse, we just flip-flop the x and the y values. If the point -2, 4 is on f, the point 4, -2 is on the inverse. -1, 1 becomes 1, -1 for the inverse. 0, 0 flip-flopped is still 0, 0, same with 1, 1. But then here we have 4, 2 instead of 2, 4. Here's where our problem lies. If I were to graph this, and I could real fast, but you'll notice that this is not going to be a function. It will not pass the vertical line test because we have inputs. That's not a great, let me try that again. We have inputs like 4 that had 2 outputs, or like 1 had 2 outputs. So the inverse is not a function, even though the original problem, x squared, y equals x squared, is a function. So parabola, we already know that that's a function, but its inverse is not a function. So that leads us to the horizontal line test. A vertical line test tells us whether or not a relation is a function. A horizontal line test tells us if its inverse is a function or not. So because a parabola does not pass the horizontal line test, that means its inverse is not going to be a function. That doesn't mean it doesn't have an inverse. It just means the inverse is not a function. So even though a parabola is a function, it does not pass the horizontal line test, which means its inverse is not a function. So here's what we typically do. We change the domain so that it becomes a function. So now it says f of x equals x squared and x is greater than or equal to 0. That means we only want to include the numbers that are greater than or equal to 0 into our domain. So 0, 1, 2, I'll even add 3, 3, 9 is on there. So I'm going to erase the left half of this parabola. We only want the right half. We only want where x is greater than or equal to 0. If it would have said x is less than or equal to 0, that would have also made the inverse a function, but we would have erased the right side of the graph and kept the left side instead. So now my parabola isn't a full parabola, so now it passes the horizontal line test, which means its inverse will be a function. So now we don't want this whole x squared thing going on, or this whole sideways x squared thing going on. Let's actually find this inverse function. So f of x equals x squared. If I flip-flop the x and the y, I get x equals y squared. And to isolate the y, I'm going to take the square root of both sides. Typically, what we do here is we take plus or minus sign, the square root of x. But that plus or minus sign is what made the inverse not a function. Because we only wanted the right side of the graph, I'm not going to call it y, I'm going to call it the inverse of f. Our inverse function is only going to be the positive square root of x. So we got rid of those first 2 points of our x squared because they had a negative in the domain. So now we're only using 0, 0, 1, 1, 4, 2, and then that last one would be 9, 3. So now that our original function passes the horizontal line test, our inverse is a function and it passes the vertical line test. And just like on that first graphing example that we did, these two functions are a reflection over the line y equals x. So let's talk about how to know if the inverse is a function. We really are just asking ourselves, if I were to graph this, does it pass the horizontal line test? And that graph would look something like this. It's like a cubic function, but moved up 1 in a vertical stretch of 2. And it does pass the horizontal line test, which means its inverse is a function. So let's find the inverse function. So step 1, flip-flop your x and your y. And then we're going to isolate the y. So in this case, we're going to subtract 1 first. Then we're going to divide by 2. And then we're going to take the cube root. And I'm going to write that as an inverse function now. So the original function was called f. So the inverse of f is the cube root of x minus 1 over 2. I'm not going to worry about rationalizing that denominator. So this is a square root function. If we were going to graph it, it's going to be moved to the right 3 and have a vertical stretch. But a square root function looks like that. And it does pass the horizontal line test, which means its inverse is a function. So let's find it. Flip-flop the x and the y. First step in isolating the y is to divide by 2. Now we're going to square both sides to get rid of that square root sign. That becomes x squared over 4 equals y minus 3. Last step to isolate the y is to add the 3 over. I'll leave it like that. There's a few ways we could simplify that or write it differently, like 1/4 x squared plus 3. Or you could even get a common denominator there. That's our inverse function. So there's one exception to the rule of flip-flopping the x and y and solving for y. And that is when you have real-world context or your variables stand for specific units. You do not want to flip-flop them. So in this case, it says find the inverse of this model. This model being, we're talking about a resistance band. R is the resistance in pounds. L is the length of the band in inches. Those stand for specific things. So if I were to flip-flop them, this is no longer true. The length of the band is not 3/8 times the pounds minus 5. No, it's the other way around. So when the variables have context, we do not flip-flop them. All we do is we solve for the variable that is not currently solved for. So right now, R is solved for. R is isolated. So when we're finding the inverse, I'm going to isolate the L instead. So step 1 is to add 5. Step 2 is to multiply both sides by 8/3. And this would be considered the inverse function because we just undid every step. And now it's written in terms of the length of the band instead of the band's resistance. And that would be helpful to us in this case. It says use the inverse function to find the length. So if we're searching for length, it's helpful to have it in terms of length. And it says that the band provides 19 pounds of resistance, which means R equals 19. So 8/3 times 19 plus 5 equals the length. 8/3 times 24, that's going to be 64. And my length is in inches. So last couple examples of finding inverses in case you need to see a couple more. We just flip-flop our x and our y and then isolate the y. So in this case, subtract 4, divide by -1, and then take the cube root of both sides. Because my original function was called f, I'll call this one the inverse of f. And it's the cube root of -x plus 4. One more. Flip-flop your x and your y and isolate the y. In this case, we will multiply both sides by 27 to get rid of the 1/27th. Take the cube root of both sides. And that can be simplified. The cube root of 27 is 3. But we can't take the cube root of x. So our inverse of g is 3 times the cube root of x.